Okay, good morning, all of you. Today we are going to start on the thermal properties of material, basically the radiation part. So let me write it. So we'll study today thermal radiation, and in thermal radiation, first of all, like to write some basics here. So all materials contains charge. So this is my first point. All materials they contain charge. So charge at motion creates, sorry, charge at rest. Charge at rest creates electric field. Then charge at constant motion, that means it is the current and it is steady. So it creates magnetic field. So this is as per Coulomb's law, and this is as per Biot-Savart's law. So next is charge at I would say random motion, that is not steady, or I'll write not steady, creates both electric field and magnetic field. So this much we basically discussed yesterday. So what we are going to do it from today is that we'll see that when a material is heated, charge moves randomly. That means electric field, that is time varying, and magnetic field, time varying, is created. That means we call it radiation. Radiation, I would say electromagnetic radiation is created due to thermal motion. So this is called thermal radiation. Thermal radiation basically corresponds to, let me copy paste the electromagnetic spectrum. So so you can see that this is the spectrum of electromagnetic wave. So we have different spectrums. These are based on the wavelength. So first is radio, second is micro, third is infrared, fourth is visible light, fifth is ultraviolet, sixth is X-ray, next is gamma. So basically energy increases in this side. So energy increases, and basically we call this infrared light as thermal radiation, because the electromagnetic waves radiated due to this thermal property, they basically come in this infrared range. The EM wave generated due to thermal motion belongs to infrared spectrum. Is it clear, all of you, up to this point? Is it
Can you
clear?
scroll a little up? Sir, I missed a line. Can you scroll a little up?
Here,
Thank you. Yeah, a little up, sir. Yes, sir. This part. Sir. Thank you, sir.
so when a material is heated, charges basically moves randomly. So whenever charge moves, there is dynamic electric field, magnetic field created. So electromagnetic field is created due to the thermal motion, and we call it basically thermal radiation. And here, all must remember that in radiation, I'll write that part. In radiation, electric field is proportional to 1 by R, and magnetic field is proportional to 1 by R. Okay, and this is the Poynting vector S, so which is basically E cross B divided by mu 0. So next thing is, these are the spectrums. So this electromagnetic wave generated to the thermal motion, they belong to the infrared. Okay, so next we are going to see what are the properties of thermal radiation. So basically the properties, first of all, thermal radiation has oscillating electric field and magnetic field. Their speed is basically 3 into 10 to the power 8 meter per second. Next, they are transverse in nature. And finally, they do not require a medium. They do not require any medium. These are the most important properties. Okay, so these are the properties. Is it clear? Okay. So next we are going to discuss on the concept of thermal radiation, basically intensity distribution. So let me copy paste the graph first. Before that, I will tell one law. So that is Stefan-Boltzmann law. So let me delete this. So I'll write so what it says, basically the intensity. It is an empirical law. Empirical law means experimental law. So intensity of thermal radiation is basically proportional to temperature power 4. So this we can write I is equal to sigma T to the power 4. So here sigma, let me write down this constant. What is the value? So it has value 5.67. So it has value 5.67 watt by meter square Kelvin to the power 4. So watt is basically joule per second. Meter you know, Kelvin you know. So this is called Stefan-Boltzmann law. It says that intensity of thermal radiation is basically proportional T to the power 4. So here thermal radiation means light. So very important concept I'm going to write here. Thermal radiation means thermal radiation is equal to light. L-I-G-H-T, sorry. And light means boson. Okay, so this, for any boson in a box, for any boson in a box, intensity is proportional to T to the power 4. This is valid for any boson. Okay, so this is a very important question. Basically, this entrance people, they ask this. Is it clear? Is it clear, right?
Yes.
Okay, so next, and another thing was, we call it Wien's law. Basically, lambda maximum T is constant. So if we see that lambda is inversely proportional to 1 by inversely proportional to T, so lambda T, and this constant has a value. Let me check that. Wien's constant. We are going to verify that Wien's, and this is a constant. So let me check the value. So 2.8 10 to the minus 3. So this value is 2.8 into 10 to the minus 3, and it is meter into Kelvin. It is meter into Kelvin. So unit is meter into Kelvin. Now we are going to verify this loss. So this is the intensity distribution. Let me discuss with you this one. This is very important. Okay. Okay. So this is y-axis is basically your intensity, and x-axis is your wavelength. It is in nanometer. So visible light is, let me write, visible is basically 400 to 700 nanometer. Okay, so you can see, and these three curves are there. This is first curve, this is second curve, this is third curve. So basically they are with increasing temperature. This is low temperature, this is high, this is high. So I basically write this is T1, this is T2, this is T3. So here T3 is greater than T2, it is greater than T1. So we are plotting a graph of intensity with respect to wavelength, and there are various temperatures are possible. So what we see that from this to this, we have actually visible light. So this is visible. Okay, and this is UV. This is UV, and mostly these are IR. These are IR ranges. Okay. So what I'm trying to say is that if you see, this is the maximum, this is the maximum, this is the maximum of the intensity. And if I connect a line, what happens? Wavelength. This is the maximum wavelength, and this is a particular temperature. So what happens? Lambda is inversely proportional to temperature. Is it clear? This is basically Wien's displacement law. It says that with increasing temperature, basically wavelength shifts towards to lower side, lower wavelength side. So let me write it. It says with increasing temperature, lambda decreases. It is observed from the graph, right? So this is basically Wien's law. And you can see that basically area is basically the total energy, right? Energy density. So if you see that with increase in temperature, the area basically increases substantially, right? So the next point is with increasing T implies area under the graph, increases. And you can see that this is not linear. This is rather T to the power 4, which we call Stefan's-Boltzmann law. So you can see that if you take any area, suppose I take this area, so this area is there. So next area is there, like I can say this area. So these areas, they basically change. Okay. So this area, they basically change, and they change very rapidly. That's why they are proportional to T to the power 4. So which is basically the Stefan's-Boltzmann law. Is it clear? Is it clear?
Yes. Yes.
So now we are going to see a violation in Stefan's-Boltzmann law. Stefan's-Boltzmann law is true, but it is still violated. So what happens when a body is heated? Implies thermal radiation. So what is the maximum temperature we can have to have? Is it possible to have intensity is equal to infinite and the temperature is very high? Because they are very proportional to each other, right? And this is called ultraviolet catastrophe. Ultraviolet, let me take that term very clearly. What we call that? So we call that so this is ultraviolet catastrophe. What it says that you can see in the graph with increase in wavelength or frequency, actually this intensity achieves a maximum value then drops. It doesn't increase to infinite, right? Means what I'm trying to say is that if I start hitting, it doesn't go up. Okay, so that is the basic reason here. Okay, so and here also this intensity doesn't go up. Here also the intensity doesn't go up. So these are forbidden actually, because with increase in temperature, it is not possible to have infinite intensity. Okay, so that is called the ultraviolet catastrophe. Okay, so let me write it down very clearly. So yeah, so I have taken this comment from Beiser book, so you all can have it. What I'm trying to say is that in reality, the energy density or the radiation rate falls to 0 as mu tends to infinite, right? Or you can take wavelength. This discrepancy became known as ultraviolet catastrophe in classical physics. Okay, so what I'm trying to say is that at high temperature, T high, that implies I goes to 0, which doesn't agree with classical physics. So this was PHYSI6. This was the major problem in the year 1900. So basically this was the discovery of quantum theory. Okay, so we have basically three proposed theories. First theories is basically your Wien's law. Basically your Wien's law. Three people they tried. Second is Ray. Let me check the spelling. Second is Rayleigh. Rayleigh. And third is Planck. So all these three people, they gave their different theories to discuss about this black body radiation. What we call this is as a black body. So let me discuss about black body. So black body is basically a perfect observer, and it doesn't actually revert back any kind of radiation. It actually absorbs everything whatever you throw at it. So let me do a black body. Yeah, so this is actually, you can imagine this as a black body. So this is a black body. So whenever you actually incident anything on it, it actually absorbs, and everything is, it is a perfect actually, this incident ray will actually reflected back and forth. Okay, so and this is the case, a hole in the wall and excellent approximation of a black body. There is a hole, and here there is a hole and incident waves, and it gets reflected all the side and it never goes outside. Okay, it is trapped actually. So light, so what we are going to study, we are going to determine the energy density inside the black body. Okay, so we are going to use three formulas. So how we are going to do that? So we U mu D mu is basically G mu E average and then D mu. What is the formula I'm writing is that energy density energy density in the range mu to mu plus d mu is equal to density of states multiplied by average energy multiplied by d mu. So here I can also multiply d mu here. Okay. So density of states means you can take it as a partition function. So the total number of states multiplied average energy multiplied d mu. So this is the total number of states multiply energy total energy, and in the range e to d mu. So this is the expression. Is it clear? This formula whatever I have written. Is it clear? Okay. So we are. I will write something, and we'll derive that. We'll derive that basically density of states. So I'm writing something. Please. Okay. So this thing will derive in a more general way, but I'm writing it here now. So this is the expression for density of standing waves, because we are allowing the light to fall inside a black body. So basically black body inside light means it is a wave. So whenever they reflect in each other, they create the standing wave. And this is the basically the density of standing wave means it is the number of waves in the energy range E to d mu. So it is basically the meaning is number of standing waves in the range mu to mu plus d mu. So here G is here we have G taken as the density of states. So mu is the frequency, C is the speed of light. C is basically speed of light. Let me consider first the Wien's law. Okay, we'll consider Wien's law first. So we'll use the same formula. U mu d mu is basically density of states, then average energy, then d mu. So if you call about this formula, this is 8 pi mu square by CQ. Average energy in Wien's law is basically e to the power minus h mu by kT, and this is d mu. So E average is proportional to e to the power minus h mu by kT. So this is empirical. So I can't derive this. This is empirical. He actually took this formula. So you can see that what is the main conclusion we have? The main conclusion is you can see that U mu d mu is proportional to which power of frequency? Can you tell me? Which power of frequency? Anyone? U mu d mu is proportional to which power of frequency?
Square, sir.
So mu to the power square. That means intensity is proportional to mu square, and if mu is very high, I is basically infinite. So this is actually ultraviolet catastrophe. It says that this is your intensity and this is your wavelength. So it will go like this. So it doesn't actually come back to the ground. So it is actually not like this. So this Wien's law is basically valid for high frequency. Wien's law valid for low frequencies. low frequency or high wavelength. So this is not valid here. Okay, so this part it is valid only. So this is the part it is valid. Okay, is it clear now?
Yes.
Is it okay? So next, Rayleigh jeans come. So Ray R A Y L E I jeans. So I am going to write for reagents U mu D mu. So density of states multiplied by average energy multiplied by d mu. So he took 8 pi mu square by CQ. This is fine. Again, he took what is the average energy of a classical harmonic oscillator. He considered light as a classical harmonic oscillator. I am writing. So light is equal to boson. That time boson concept was not there. So I'll write light as a classical harmonic oscillator. So what is the average energy of a classical harmonic oscillator? Per degree, how much freedom? Half kT. This is for kinetic. This is for potential. So the total energy is basically classical harmonic oscillator is K. K is Boltzmann constant. Is it clear? So I'm going to put that KT here and multiplied by d mu. Okay. So this is basically your Ray-Jeans law formula. So it also have the problem. So, you know, this is also violates the ultraviolet catastrophe. So it has also the problem. Okay. So this is actually the Ray-Jeans law formula. Next, Planck came. What he did, U mu, D mu, then G mu, E average, then d mu. So what it took, 8 pi mu square, this is constant, by CQ. So this average energy he took, h mu divided by e to the power h mu by kt minus 1 d mu. So he took average energy as a quantum harmonic oscillator. Okay, so this is average energy of quantum harmonic oscillator. So this formula basically took care the complete profile of the intensity distribution. So this is the third formula. This is the second formula. And this is the first formula. So whenever he put this formula, now tell me, very important note here. What is energy is proportional to? So it is proportional to frequency, right? Right? You understand my point? Energy is proportional to frequency. So that's why Planck actually predicted this formula. So you almost not confuse that this formula comes from arbitrary. It came from this Ray-Jeans and all this conclusion means energy is proportional to frequency. So basically first order. So this is basically quantum harmonic oscillator. Quantum assumption, I will say. E is equal to nh mu you have. So h is basically your Planck's constant. Is it clear?
Yes.
Okay. So these are the three formulas, and due to this, they were actually able to understand the complete radiation. So I'll just black body radiation. second. Copy image. So this is the basically the intensity distribution. Always remember this graph because this graph has come in entrance examination many times. Okay, so this is actually the use of Planck's radiation formula. Okay, so U mu d mu is equal to 8 pi mu square by CQ h mu e to the power h mu by kt minus 1 d mu. So this is valid for all bosons. Valid. And this lambda t is valid. This is constant. Wien's displacement law. So you can see that decrease in lambda peak with increasing. This is Wien's law. And there are temperatures are there. Increase intensity with increase in temperature. And wavelength intensity. This is the general Planck's actually predicted means the theoretical formalism, and this actually matched with this real thing. Okay, real the graph. Okay. So now, any doubt into this? Any doubt into this? Okay. So next is, let me check. I basically used the book from Beiser. Okay, this is the reference I took. So I'll write some points which you must write it. So apart from this radiation, there are other two effects. So I'm writing it here, light, wave, right? Sorry, I'll write a comparison, right? So previously wave, and this is now particle. And we will take the example of light, LIGHT. So in wave can propagate, wave can be absorbed, wave can be transmitted. So all these properties has to be satisfied in particle form. So wave must propagate, wave must absorb, wave must transmit it. Okay, so here this is actually black body radiation. This is the experiment that shows that light is actually absorbed in form of packets. Transmitted is basically, if you see light is absorbed, transmitted, it is actually Compton's effect. And sorry, emitted, sorry, I forgot, it is emitted. Let me write it completely. I think let me one minute. Emitted, transmitted. So this is emitted. So 1-to-1 correspondence we are going to make. So propagate means Compton's effect. Absorb means photoelectric effect. Absorb means light. Yeah. Emitted means black body radiation. So these are the experimental verification, A experiment. Okay. So what I'm trying to say is that apart from black body radiation, there are other two effects which supported that light are also quantized in nature. So like wave propagates, light is also propagate in terms of particle. So that is called Compton's effect. means it can collide with other electrons, it can change the wavelength. Then coming to the absorbed part, light can be absorbed. So that is a photoelectric effect. When electron absorbs energy, you know that for when energy is absorbed, electron is emitted. So that is photoelectric effect. When in black body radiation, energy is actually emitted in form of quantas. Means it is the radiation. Okay. So all the properties of the wave are basically satisfied in the properties of the particle. So light can behave as a wave and it can behave as a particle. Okay, so these are the major comparisons we see. So mostly in GATE or NET they ask this question, what are the nature correspondence in particle and wave. Okay, so do you get some idea here? Okay, so from next class we will do the derivation of the density of states. So I'll write it. So next class, so to be done, so derivation of density of states, that is basically 8 pi mu square by CQ. This formula we are going to derive. This is the partition function we are going to derive. So you can take a leave, or if you have any doubt you can ask me.
So can you discuss the intensity distribution graph again?
Okay. So this is the intensity distribution of any thermal object. So whenever you heat a sample, thermal energy is radiated. If you heat more thermal energy is radiated. This graph basically shows the intensity of emitted radiation with respect to that particular wavelength, right? So why wavelength means whenever we heat a substance, basically we emit electromagnetic radiation, and we are talking about this the electromagnetic waves wavelength, right? So this is my object. So this is my object. It emits radiation, and we are talking about wavelength, and we supply heat to it. So this is the temperature. So this is the temperature. So we are plotting this graph at different temperature. So T1, T2, T3, T4. So this is in greater order. Okay. So T4 is greater than T3. It is greater than T2. It is greater than T1. And these are the higher temperatures. Okay, so this is the lowest temperature. You can see at low temperature area under the graph is less. At high temperature, as I increase, the area under the graph is increasing. That means my intensity is basically increasing, right? So whenever I say u mu d mu, that means area under the graph. This is clear, first of all. Is it clear? Okay, so next thing is you can see, sir, for a particular thing, let me draw that graph for you. So what is happening? So this is my u mu and this is my mu, right? So I think I guessed. Okay, so what is happening? So this is actually going like this. So what actually we are thinking that if we go to infinite temperature, basically we must go for infinite energy, right? But this is not happening. That's why we call that ultraviolet catastrophe. Okay, so our theory cannot, because this is experiment and this one is basically theory. So theory says it should go like this, because if we increase the temperature, energy should increase, it will go. But this is not happening. What actually happening is that actually the graph comes to ground. Okay, so this is actually the total energy. right? This is the area under the graph. Okay, so what is happening with increase in temperature? So this is one case, this is another case. The maximum of this wavelength, okay, basically inversely proportional to the temperature, that we call Wien's law. And this area under the graph is called the total energy radiated by the body. Okay, and with increase in temperature, energy density or the area basically increases, which we can see from the graph. Okay, what this ultraviolet catastrophe is that it must go like this because intensity is proportional to mu square as per Wien's law. Okay, so this graph, in conclusion, it says that first of all, I'll write in conclusion. First of all, first conclusion is this is the experiment, right? So it says area under the curve is basically the total energy. So I mu, so it is the total energy. So this is total energy released. Okay, and this is basically lambda max. This is the maximum range, maximum wavelength. It can, this is the maximum, you know, you can know from a graph, you can have an average, you can have a maximum, you can have most probable. So this is the maximum. And if we increase the temperature, wavelength will go to the lower hand side. So this is the Wien's law. Is it clear?
Yes.
Okay. So any other doubt you have, you can ask me.
The part you mentioned that when a body is heated, it's basically thermal radiation, and the infinity as infinity, the intensity as is at infinity. That's what you done.
Okay, okay. So as per this Wien's law, I'm writing the formula again. U mu d mu is basically 8 pi mu square by CQ, and it is e to the power minus h mu by kt. This is Wien's law. Okay, this is experimental law. That means this intensity, this is the intensity. Intensity is proportional to mu square. So if we plot the graph, it will go like this, right? The theoretical curve is, it will go like this. So actually in experiment, we observe this is like this. So this is basically ultraviolet catastrophe, UV catastrophe. Okay, so from theory, we see that intensity is mu square. So if we go to mu infinite, what will happen? I must go to infinite, right? So this thing is not happening actually reality. It is actually dropping back. So that's why this is called ultraviolet catastrophe. Okay.
Yes.
Any other questions or suggestions?
Yes.
Okay, if there is no, then you can take a leave.
Thank you.